This is the solution to chapter 16 video assignment 2. The question states, in this problem you're going to calculate microstates and configurations for dice. We use 6-sided dice. You have 3 dice named A, 2, and Z. It's like Cyrillic alphabet, I don't know. The configuration for the dice is the sum total of the 3 dice, and the microstate is which die has which value. The configuration is therefore ranged from 3 all 1s to 18 all 6s. Using our S equals K natural log W entropy equation with K equaling 1, calculate the entropy of each different configuration in their 216 microstates. So we can visualize the configurations of microstates using this little diagram here. We have our 3 dice with each of the 6 numbers that they could be. And so for the first configuration, it's 3, right? The configuration is equal to the sum of the dice. And so each one can have 1, and that will equal to 3. And so the microstates are going to increase more and more and more for the increasing number of configurations. So for example, for a configuration of 4, we could have 1, 1, 2, or we could have 1, 2, 1, or we could have 2, 1, 1. And so those are the 3 different microstates applicable for that configuration. And so the first 3 I could do in my head for the configuration of 5, there's 6 different microstates because you could have 3, 1, 1, 1, 3, 1, 1, 1, 3, or 2, 2, 1, 1, 2, 2, 2, 1, 2. Right? So those ones that would come in my head. Okay, there's this different microstates for these configurations. For the higher number configurations, it took a little bit more writing down. So basically what I did was just write down all the different combinations of dice that it could be. For example, for 6, we could have 2, 2, 2, or 3, 2, 1, 1, 3, 2, 3, 1, 2, so on and so forth. I wrote them all here in my notebook, as you can see. But for sake of space on the whiteboard, I only wrote a couple. So I'll just go over at 10, how I determined that. Just started at 6. So 6 to sum up to 10, you'd have to have a 3 and a 1. And then you can swap those 2 numbers. So 6, 3, 1 could be 6, 1, 3. Using a different number in this little data set, you could do 3, 6, 1, 3, 1, 6. Using the 1, 1, 3, 6, 1, 6, 3. Then moving on to 5, 5, 4, 1, 5, 1, 4, 1, 5, 4, 1, 4, 5, and then so on and so forth, moving on to 4. Just going down in numbers until I had all 27 microstates that are possible for that configuration. Now I'm sure there's probably some kind of programming you could write to solve this faster, but I don't know how to program, so brute force works just fine. So those are all the different microstates. Oh, another piece I forgot to mention. Because of the nature of the dice, okay, here we go. There's 15 different configurations it can be, right? 18 minus 3 is 15. So this goes halfway. This goes up 8 configurations to 10. Now, because the nature of the dice and configurations of microstates means that the numbers in the middle, the configurations in the middle, are going to have the most microstates, we can assume that perhaps it's symmetrical. Now, to test if it is symmetrical, I just looked at 18 and thought, okay, 18 has to be 666. There's only one possible microstate for that. For 17, you'd have to have 665 or 656 or 566, which would be 3. The same held true for 16. So because this pattern matched that pattern, you can correctly assume that it's symmetrical. So 11 will also be 27, 12 will be 25, 21, 15, so on and so forth, right? It's just a mirror image going up to 10 and then down, and then forward from 11. Up to 10, forward from 11 is symmetrical. And summing all those up, it equals 216, further confirming that it is indeed symmetrical, and these are the microstates associated with all of the different configurations. But the question doesn't just ask for microstates, it wants to know entropy. And so the formula for entropy is S, which represents entropy, is equal to K times the natural log of W. And for the sake of simplicity, thank goodness we're setting K is equal to 1. So S is just equal to the natural log of the microstates. So 1 is 0, 3 is 1.10, 6 is 1.80, 10 is 2.30. To save you writing on all these, we just have the solutions here. 2.71, 3.04, 3.22, 3.30. And obviously it's symmetrical again, so we get 3.30 again, and 3.22, 3.04, 2.71, 2.30, 1.80, 1.10, and 0. And so just by solving for the number of microstates in each configuration, by considering each different arrangement of dice, and then by plugging those values into the equation for entropy, we're able to solve for the entropy of each of those different configurations of 3 6-sided dice.